Let's take a look at Dijkstra's algorithm. So it takes a graph, a weighted graph, and a start vertex. We can only compute the shortest path if we say the shortest path from where. We're going to have a set of vertices that we have that are found and a set that are not found. So to begin with, everything has not been found, meaning we don't know the shortest path to those vertices. In prior algorithms, I denoted this a little bit differently. Instead of having a set here of found, we did something like say that each vertex was false, meaning it hadn't been found, and that was for for all vertices in V. We're doing this a little bit differently this time because we want easy access to the vertices that have already been found. Turns out that that's going to be useful to us. So that's now going to be a set instead of a dictionary that we do a lookup in. So we're just going to be adding to that set and looping through it actually. We'll have a length of each path, so we'll initialize those all to infinity for all vertices. We're going to add the start vertex to found, and we're going to set its path length equal to 0. Next, we're going to loop until our found set contains all vertices. So one way to do that is, what is the length of this thing? When the length of that thing is equal to the length of this thing, which is all vertices, we're done. We could also just say when found equals the vertices. That's a little bit harder to do, to reason about in code, so I like to be a little more explicit here about what we're actually doing. Okay, so this is why we put found in a set instead of a dictionary. We're going to loop through each vertex that's already been found. So what you should think about for Dijkstra's is it's kind of like breadth first search. We have our start vertex, and then we find all of the vertices that are sort of cheap to get to from there. So maybe we have something that looks like this, and maybe these are all the vertices we found so far, and now we want to look at all the vertices that are connected to those. So we want to loop over A, B, and C and see what they're connected to and see what's the cheapest next path. So now we're going to loop over all of the vertices connected to each V and call those V other. And at the same time, we have to pull out the weight. If V other is not found, well, that's a candidate edge. So it's one that we could be marking the shortest path for. So we're going to compute the shortest path. And the shortest path is, well, what's the length of the path to get to V plus the weight of this current edge? So if I have my start vertex and I get all the way down here to vertex L, and here's vertex X, well, we could say that one path from the start vertex to X is to go from S to L. Let's say that has a cost of 15, and this edge here has a cost of 4. Then it would take a total cost of 19 to get to X. So that's really what we're computing here, where this length would be that, and this weight would be the weight of that edge. And that has a special name. So that equation there, length V plus weight, is called Dijkstra's greedy criterion. Whoops, greedy. And it's special because we've already computed the length of the path to V. So we're reusing information that we've known from before. And if that happens to be the shortest path length we've seen so far, and I realized as I was going through these slides again that I forgot to initialize the min length. So I was just lazy and try to remember, I'll put that in here somewhere. That min length initialization should really go right in here. So it starts out at infinity, and we're just trying to say, do we find something less than that? So is this length to V other less than infinity the first time around, or in subsequent iterations just less than what we just are computing here? Is that the cheapest path length we've seen so far? If it is, we'll hold on to it. So we'll say min length is equal to that length, and we'll hold on to that vertex that we're connected to. We'll call that vertex V min. And then at the very end of this for loop, we will have compared a bunch of candidate edges right here. We'll grab the cheapest vertex and add it to our found set, and we'll set the length of the path to that vertex equal to V min. At the very end of our algorithm here, we just have to return all the lengths. So again, we're not going to care about the paths themselves. In class here, we're just going to compute the lengths. It's not too much extra work to compute the paths themselves. If we know that the length of the path to get to V is here, then we'll talk about this later in the semester, but we could come up with an idea of a predecessor. So what's the vertex that comes before this vertex? So the predecessor of V min would be whatever the V is right here. And then we can backtrack all the way to the start vertex. But I don't want to put too much code on here for the first time we look at this particular problem. Okay, so at any given stage, this is what we're looking at. We have a set of vertices that we're going to say are already found, and that includes the start vertex. And we have a bunch of vertices that are not found, so that would be the vertex set over here, V, minus those that are in found. As we loop, this would be V, this one would be V, this one would be V, and V other is going to be any of these that are over here on the right-hand side. Well, actually, our code will consider those on the left-hand side too, but we just don't go into this if statement here. So we're going to compare, and we're going to look at the shortest among all of these paths, the ones that are in purple here. All right, well, let's go through an example of this on the graph I have above. So let's mark the start vertex as 1, just because, you know, this graph sort of flows from left to right. I think it makes sense to make the start vertex 1. So we'll add 1 to our set found here. We'll set the length of the paths to every other vertex equal to infinity. I already added 1 to the start vertex, and we'll say, or to the found set, and we'll say the path length to get to the start vertex is 0. Now we jump into the while loop, and we loop over everything that's been found, which is right here. That's only the start vertex currently. So inside this for loop, in iteration 1, we're going to say V is equal to 1, and then we're going to say V other is equal to 2, and we're going to compute the length to that. So let's just call that L here. I've got it V other length, but I don't want to do too much writing here and run out of space on the slide. So the length of that path is going to be equal to the length to get to V, which is this 0, plus that edge, which is 1. So that's going to be equal to 0 plus 1 is 1. So that's one edge we consider. We also consider in the next iteration V other is equal to 4, and the length of that one is equal to, I'm sorry, it's vertex 3, the path, the edge weight itself is 4. So vertex 3 and 0 plus 4 is 4. And in this loop, this innermost nested if statement, we compare those values. So we're going to take the minimum of those, which is this one, and we'll add 2 to our found set, and we'll mark the path length to get to 2 equal to 1. So that's the first iteration. And the second iteration, we're going to do the same thing. So currently we have 1 and 2 in the found set. We have a path length of 1 to get here, and infinity here, and 0 here. In iteration 2, we now have 2 vertices that we loop over from the found set. So we'll say that V the first time is equal to 1, V other is equal to 2. We just skip that one because we've already computed it. It's already in found, as shown here. V other is now 3, and we're going to compute that length, same as before, it's 4. So you can cache those values if you don't want to recompute them every time. And that's everything connected to 1. Now we have to look at everything connected to vertex 2, because vertex 2 is also in the found set. So the things connected to vertex 2 are 3, which is going to give us a total path length of 1 plus 2 is equal to 3. And vertex 4, which has a total length equal to 1 plus 6 is equal to 7. What's the cheapest out of all of these? So we're going to compare the 4, the 3, and the 7, and the 3 is the cheapest. So we would say that the next thing we add to our found set is vertex 3, and its path length is no longer infinity, its path length is a total of 3. And then in the next iteration, we would find that to get to vertex 4, we would have a total cost of 6. All right, so now here's a good place for me to break this video and encourage you to work on the exercise for this set of lecture slides.